OCR Chemistry A, phenols and further substitution. Getting the most from Chemistry Explained means taking notes and completing tasks on paper or on a tablet, controlling the pace at which the lesson proceeds. Particularly when prompted, pause the lesson, complete the task, thinking it through, taking your time. When you're ready, return to the lesson and correct your work before proceeding. So let's start with the acidic properties of phenol. We'll then move on to the electrophilic substitutions and the relative reactivity compared to benzene, and then consider how a substituent on the benzene ring directs the position of second and third substitutions. So here is the structure of phenol. Benzene ring, hydroxyl group directly bonded to the carbon ring in benzene. I've also highlighted the fact that the oxygen of the hydroxyl group has two lone pairs of electrons, and these lone pairs of electrons are influential on the chemistry of phenols, which we'll go on to explain and discuss. So we'll start with some straightforward acid-base properties of phenol. And phenols differ from alcohols, so it's important to realize phenols are not classified as alcohols. They differ from alcohols in that they are slightly more acidic than water. So in other words, they are weakly acidic, and a typical solution will have a pH of around between 5 and 6. The fact that they are weakly acidic means they are neutralized by sodium hydroxide in a typical acid-base reaction to form a salt, which we are going to call sodium phenoxide. So if I give you the structure of phenol and sodium hydroxide, please pause the lesson and complete the product side, including the structure of the sodium phenoxide ion formed. Come back when you are ready to check against my answers. Okay, so here is sodium phenoxide. We've got a sodium ion from the sodium hydroxide, obviously. The hydrogen from the hydroxyl group has been donated to the hydroxide ion to make water. So Bronsted Lowry acid, we're going to donate a hydrogen, we're going to donate a hydrogen ion or a proton to a base, a proton acceptor, to form water in this case. Now, it's this bond here, the oxygen-hydrogen bond, that is acidic. It is this bond that is broken. The hydrogens present in the benzene ring are not acidic. It's purely the hydrogen here of the hydroxyl group. So we would say phenol is monobasic. The phenoxide ion formed here is a 1 negative ion. The pair of electrons that were in the oxygen-hydrogen bond here are now positioned on the oxygen. It has a negative charge. Hence, the sodium ion will associate in an ionic compound sodium phenoxide. So phenols will neutralize sodium hydroxide, an alkali, and therefore they are more acidic than alcohols, but they are less acidic than carboxylic acids and will not react with carbonates, whereas carboxylic acids will. So if we look at an example of a carboxylic acid, ethanoic acid, that will react with sodium carbonate according to the equation that I have partly written out. Could you pause the lesson and complete the reaction equation for ethanoic acid and sodium carbonate. Come back when you are ready. So here are the products. We've got 2 sodium, so we're going to get 2 sodium ethanoates, carbon dioxide and water, the classical fizzing of an acid with a carbonate. So carbon dioxide is the gaseous product. The salt, sodium ethanoate, and of course we need to balance with 2 ethanoic acids. But, as I stated a little earlier, phenols and carbonates, there is no reaction. So the OCR A specification requires you to distinguish between the acidity of phenols and alcohols and phenols and carboxylic acids. Phenols are less acidic than carboxylic acids, but more acidic than alcohols. How would you demonstrate knowledge to justify that statement? Well, phenols do not react with carbonates, whereas ethanoic acid, for example, does. And phenols do neutralize sodium hydroxide, whereas alcohols do not. So phenols are weak acids, we've established that, and that means the position of equilibrium in the acidic dissociation lies well to the left. So here is phenol, here is the phenoxide ion. It has lost a proton. The equilibrium lies well to the left. Phenols are weak acids. However, phenols do lose a hydrogen ion, whereas alcohols are not expected to. And that is because, pause the lesson and see if you can come up with some reasons why it is that the phenoxide ion here has some appreciable stability. Come back to discuss further. Okay, so the phenoxide ion formed here an electron pair, which I've indicated by 3 pairs of dots, from an oxygen atom, from the oxygen atom. Those electron pairs are in a p orbital. They are able to overlap with the p orbital system, overlapping p orbital system of the benzene ring. And that means those electrons may be delocalized throughout that system, and therefore the negative charge, which in my diagram is located on the oxygen atom, is better thought of as being delocalized over the entire molecule structure throughout the whole pi, the delocalized pi system, which now includes a p orbital from the oxygen atom. An orbital diagram is helpful to explain this. So here we have our 6 carbon atoms, each with a p orbital that overlaps to form a delocalized pi system above and below the plane of the molecule. You've seen this diagram before. That can now include the p orbital on the oxygen atom, so that this charge is now delocalized. That is, a pair of electrons in the p orbital are able to move throughout this overlapping p orbital system. So a pair of electrons in this p orbital can move above and below the plane of the benzene molecule throughout there. So they are delocalized. And as we said earlier in the aromatic chemistry, delocalization means greater stability. So increased stability. So rather than the electron pair being located on the oxygen atom, as is shown in my diagram, that electron pair in the p orbital overlapping with the p orbitals of the carbons within the ring those electrons are able to be delocalized throughout the pi system, and therefore delocalization is associated with greater stability. So the phenoxide ion is stabilized by delocalization of the charge. Moving on, let's look at the electrophilic substitutions of phenol and the relative reactivity of phenol compared to benzene. So moving on to the reactions of phenols, they of course are electrophilic substitutions, and we can find or show that phenols react more readily with electrophiles than does benzene. So if we look at a first example, which would be bromination, then for the full equation we see phenol and 3 bromines react to give you a tribromo compound, and obviously as a waste product 3 hydrogen bromides. But we'll contrast that reaction with the reaction with benzene, which went to the mono halo product. Pause the lesson and name the product of the bromination of phenol. Come back to check your answer. Okay, so here is the name, 2,4,6-tribromophenol. So we're saying carbon number 1 is where the hydroxyl group is attached to the benzene ring, so that's naming it as a phenol. Carbon number 2, 3, 4, 5, 6, or if you prefer 2, 3, 4, 5, 6. So 2,4,6-tribromophenol. Now the conditions are the crucial feature here. The conditions are room temperature and aqueous bromine. Room temperature and aqueous bromine. Now cast your mind back to the reactions of benzene with bromine, the bromination of benzene. What were the conditions for that? If you're not recalling those conditions, check back through your notes before we go on to the next slide. So let's take a second example, nitration. So here is phenol and here is nitric acid. The reaction proceeds on a 1-to-1 ratio between phenol and nitric acid, but there are 2 positional isomers formed. With your knowledge of bromination of phenol, looking back at the structure of the product there, suggest the structures of the 2 positional isomers for the nitration of phenol. Pause, come back when you have thought it through carefully and written down 2 possible structures. Okay, well, here are the 2 structures. We've got one nitro group joining on position number 2 and another on carbon 4 in the phenol molecule. So if you look back at bromination, the pattern was for phenol further substitutions 2,4,6. So position number 2 and position number 6 are equivalent in nitrophenol. Position number 4 is not. So the 2 positional isomers would be the 2 molecules as I have drawn. Pause the lesson and name them. Okay, so here are their names. 2-nitrophenol, I hope that's not a surprise. Carbon number 1, carbon number 2, and of course 4-nitrophenol, carbon number 1, carbon number 4, so 4-nitrophenol. Don't forget to balance with water. I've said 2-nitrophenol or 4-nitrophenol. They are made on a 50-50 basis. They are equally energetically likely to form. But what about the conditions? Well, the conditions for the nitration of phenol are 25 degrees Celsius, that is room temperature, and dilute nitric acid. So cast your mind back. What are the conditions for the nitration of benzene? If you're not clear, look back at your notes on that, please, before we go on to the next slide. A review of reactions, conditions, products, etc. would be useful at this moment. So what I've got here is a table. I suggest you try and fill it in, first of all, from recall. What do you remember about the product of nitration of benzene and of phenol? What is the catalyst for that nitration in both cases? What are the concentrations of reactants? What are the temperatures for a successful reaction for benzene and for phenol? Then move on to bromination. What is the product of the bromination of benzene and of phenol? What is the catalyst required for successful bromination? What are the temperatures required for successful bromination? So pause the lesson. First of all, start with recall. What do you recall of those products and conditions? And then complete by reference to your notes. Come back when you are ready to check your answers. Okay, so let's just start with the nitration. So the product of nitration is nitrobenzene, in the case of benzene. The catalyst is concentrated sulfuric acid. It is required to have concentrated nitric acid and a temperature of 50 but not above is required for the nitration of benzene. For phenol, there are two possible products, 2 or 4 nitrophenol, no catalyst required, dilute nitric acid, and the reaction will proceed at room temperature, but again, not above. Move on, if you haven't already done so, to bromination. Okay, so I'm going to reveal the bromination. So for bromination, benzene forms bromobenzene, a catalyst, a halogen carrier catalyst is required, iron 3 bromide or iron tribromide, aluminium tribromide, and that will take place at room temperature. Phenol, being much more reactive, will form the tribromophenol, 2,4,6-tribromophenol. There is no requirement for a catalyst for that reaction to proceed to completion at room temperature. Now, reflecting on those conditions and products, it's quite clear that phenol is far more reactive to and far more attractive to electrophiles than is benzene. You need to be able to recall some evidence to support that statement. However, we also need a theoretical explanation, and we'll address that in the following slides. So why is phenol more reactive than benzene? So the crucial thing as far as the OCR A level is concerned is that you make a comparison between the reactivity of phenol and benzene. And this is related to the electron density in the delocalized pi system. Now, if we look at this diagram of phenol showing the p orbitals, we can see that the p orbital is a lone pair of electrons on oxygen in a p orbital. That bond is sufficiently short for overlap to occur between the oxygen and the p orbital of the oxygen and the p orbital of the adjacent carbon within the carbon ring. So that means that the electron pair in a p orbital on the oxygen atom can be delocalized within the whole pi system of the benzene ring. So the oxygen p orbital lone pair is delocalized into the delocalized pi system. And that, of course, will increase the electron density of the benzene ring. Now, if there's a greater electron density in the benzene ring, bearing in mind that the reactions of the benzene ring are electrophilic substitutions, then phenols will attract electrophiles more strongly than benzene. So everything has to be related to a comparison to benzene. So let's move on to discuss the position, the direction of second and third substitutions into the benzene ring. Direction of further substitution, by which we mean the direction of second and third substitutions. Phenol, which we have just been discussing, directs further substitution to positions 2 and 4 on the benzene ring. So here's a nitration you have met, the nitration of phenol. Can you propose products for that nitration? 1-to-1 ratio. So propose products. Pause, come back when you are ready to compare against my answers. Okay, so I'm going to reveal 2 nitrophenol or 4 nitrophenol will comply with a 1-to-1 reacting ratio, plus of course water as your waste product. So phenol is 2 directing and 4 directing. The second substituent has been directed to position 2 or position 4 by the hydroxyl group in phenol. Now, why is that? Well, we think it's associated with lone pair of electrons on the oxygen that is directly adjacent to the benzene ring. If that's the case, try this problem. I'll just remind you that phenylamine, the nitrogen, has a lone pair of electrons, of course. Pause the lesson and see if you can come up with one organic product that reacts in the ratio, from the reaction in the ratio 1-to-2. Pause, check your answer when you're ready. Okay, so I'm going to reveal 2 nitro groups. It's dinitrophenylamine, but we would say 2,4-dinitrophenylamine, obviously balancing with 2 molecules of water. So what is the distinctive feature that we're looking for in OCR A chemistry? We're looking for the donation of the lone pair. So the lone pair can be donated into the benzene ring, into the delocalized pi system, and that controls, as we discussed earlier, or explains the increasing reactivity of phenol, and would also explain the increased reactivity of phenylamine or phenylamine, but it also explains the directing effects of phenol and phenylamine, both of which are 2,4 directing. So a quick review of other 2,4 directing substituents. You are expected to know about the hydroxyl group in phenols and the amine group in phenylamines, but there's other 2,4 directing groups which you may be given information about in exam papers. These 2,4 directing groups in general increase the electron density in a benzene ring. However, that is not true for the halogens. If the electron density is increased in the benzene ring, then the reactivity towards electrophiles is increased. That is, they attract electrophiles more strongly. However, that is not the case for the halogens. The halogens are actually electron withdrawing. None of that is on the specification. However, it might be information supplied in a question. So a little bit of forewarning will help you deal with any apparent novelty. Moving on to 3 directing substituents. So these contrast with 2,4 directing substituents such as phenol in that 3 directing groups withdraw electron density from the delocalized pi system in the benzene ring. The example you are expected to know about is the nitro group. So the nitro group is 3 directing. So if I give you this simple problem, nitrobenzene nitrated with 2 molecules of nitric acid, could you propose and draw the structure of the organic product? Pause, come back when you are ready. Okay, so I'm going to reveal. So we've got trinitrobenzene, position number 1, position number 3, position number 5. Now you'll notice that 3 and 5 have equivalence in position to position number 1. So this could be 3, this could be 5. So when we say 3 directing, it also means that we will go for, we will substitute at 3, but also at 5, because the 5 position is equivalent to 3 in relation to the initial substituent, NO2. So that molecule would be 1,3,5 trinitrobenzene. One thing to consider is that if you withdraw electron density from the delocalized pi system, then the benzene ring will be less, that molecule will be less reactive, less attractive to electrophiles. So electron withdrawing substituents tend to reduce reactivity. So to get the trinitro product here, one would need forcing conditions. A useful rule of thumb, not on the specification, but nevertheless a good aid, is that 3 directing groups tend to have multiple bonds. So substituents such as, say, a nitrile group, carbon triple bond nitrogen, would be as a substituent on a benzene ring, would be 3 directing. In which case, try this problem. Benzene carboxylic acid plus 1 molecule of nitric acid. Predict the nitration product. Pause, come back to compare your result with mine. Okay, so here's my proposal. 3 nitrobenzene carboxylic acid, or 3 nitrobenzoic acid. Have to recall that the COO is the carboxylic acid group that has a multiple bond in it, so that would be 3 directing. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.